Okay, folks, some people have asked for me to go do a bit of a walkthrough through question 18 of your paper 1 preparation pack, which is about equilibrium. So I thought I'd just do a quick walkthrough and share it with all of you. So it's about equilibrium. We're asked to work out the number of moles of E and the number of moles of F at equilibrium. So, there we go. How do we go about doing this? Well, it tells us at the start we've got 2 moles of E. So we've got 2 moles of that, and we've got 1 mole of that. And then at equilibrium, it tells us we've got 0.8 moles of G. So I need to know now exactly how much E and F has reacted to know how much E and F is left at equilibrium. Well, it's the ratio now, because you got to look at the ratio of G to F and E independently. So what is the ratio of that to that? Well, it's 2 to 2, isn't it? So if 2 moles of this reacts, 2 moles of this forms. So if 0.8 moles has formed, 0.8 moles must have reacted, which gives us 0.2 left over. And then you can look at it from G to E. Now this ratio here is 1 to 2. So 1 mole of this will form 2 moles of G. So 0.8 going backwards, 2 to 1, means 0.4 must have reacted. So I end up with 1.6 overall. So it's 1.6 moles of E and 0.2 moles of F. Okay, that's the first part done. Expression for Kc, products on top, reactants below, products on top, reactants below. Right, just remembering the little ditty. So, products on top, so that's G, concentration of G squared, divided by concentration of E times the concentration of F squared. And to work out the units, you just need to know how many concentration terms you have on top and how many you have underneath. So you can clearly see I've got 2 brackets on top and 3 brackets underneath. So effectively I'll have, let's get that error out of the way, that. So I can cancel that with that with that. So I end up with 1 divided by moles per decimeter cubed. So when I'm bringing, that's the inverse of what we need. So I need to bring that to the top. So mole to the 1 becomes moles to the -1, and decimeters to the -3 becomes decimeters to the +3. All right. Common mistake here where people get very excited is that they get a question like this, question C, and they just think they need to put all the numbers in, all right, which is not quite true yet, because you're given the number of moles of E, moles of F, and moles of G, and a volume. Well, they wouldn't give you the volume unless you didn't really need to use it, So you have to convert your number of moles into concentration, so N divided by V, so, and then put them into Kc. So overall, the expression for Kc is 0.85 divided by volume squared divided by 2.5 divided by volume times 1.2 divided by volume squared, and you should end up with 0.301. Okay, right, this next question, all right, so the mixture in part C was allowed to reach equilibrium at temperature T1, different container of volume 3 decimeters cubed. So what's happened here to get, and I've done this sort of over here, all right, to get from question C to question D, I've gone from a 1.5 decimeter cube flask to a 3 decimeter cube flask. So basically, I've got a bigger flask. Now that's important because by having a bigger flask, what does that do to the pressure? Well, bigger flask means that there's more space for the particles to move around in, so the pressure actually decreases. So this is crucial to accessing this question. I've got a lower pressure by having a bigger flask. Bigger flask, lower pressure. All right, so what does that mean in terms of the amount of G? Well, so I don't need to keep flipping back. Let me just write the expression again. So it's E plus 2F makes 2G. So, and they're all gases. So if I lower the pressure, equilibrium will shift to the left-hand side to make more moles of gas. So if you lower the pressure, equilibrium will try and make more pressure, i.e. more gas molecules. What effect will that have on G? Well, if equilibrium is shifting to the left, I will end up with less G. So lower pressure, equilibrium shifts to the left-hand side as there are more moles of gas on the left. So it will increase the pressure by shifting that way. So bigger flask, lower pressure. That's the key thing to take from this. Okay, right. Now, here's the sort of working out for this particular next question. So it says in the question that the value of Kc was increased at T2. So I'm just going to go through my working outs here. All right, so let's get rid of that for a minute. It says that Kc increases at T2. So at T2, Kc increases. Well, what does that actually mean? Well, Kc, I've got my expression here, concentration of G squared divided by concentration of E times concentration of F squared. So if Kc is getting bigger overall, that means that the top number, i.e. the concentration of G, must be getting bigger. So at T2, I'm getting more G. So T2, more G. So what does that actually mean? So in terms of whether T2 is higher or lower? Well, I need to actually go back to the start of this reaction, or this question, and know the enthalpy change. So the enthalpy change, I can clearly see, is minus 50. So that's minus 50 going forwards. So now I know that it is exothermic going forward. So it's exothermic going forward. So at T2, I get more G, which means it's going in the exothermic direction. So now I know that T2, for that to happen, T2 must be a lower temperature. And I'm just going to play forward Le Chatelier's in my mind now. If I lower the temperature, equilibrium will shift in the exothermic direction to try and increase the temperature again. And by going in the exothermic direction to the right-hand side, I'll get more G, which will lead to a bigger Kc. Right, so T2 must be a lower temperature. Now the question unfortunately says, which is the higher temperature? Well, the higher temperature must be T1. Why? Because the forward reaction is exothermic, so a higher temperature will favour the reverse reaction to lower the temperature. Or as it is endothermic. And that will lead to a smaller Kc overall. All right. So again, I think the quantitative questions are challenging at times, but I sometimes think the qualitative ones, the ones where you have to sort of like think about the processes, are even more challenging. So I hope that helps with that particular question.